Okay, so as we know, because I said in class before, um, we have plenty of time for the exam. That's a good thing, probably, because right now it's decompression time. From that the voting seems more complicated than this class, but I'll try to. I have to kind of like finish up a few things. So on Monday will be a class where I will devote it entirely to tell you. I'll think about the questions that I'm going to put in the exam over the weekend. So on Monday, I will have the precise instructions on the things I'm going to tell you that are going to be in the exam. I'll do the same thing I did in the first exam. I'll give you the long format problems in their entirety. But well, probably all of them. I don't know. I'll think about it a little more. Maybe I'll leave something a little bit ambiguous, but I have to figure out the timing more than anything. So I'm not really sure. Yeah, you guys take a little longer online because you have to upload. That's it. That always gives somebody some trouble. So I want to leave a little 15 to 10 minutes extra. That seemed to be about what you needed last time. The last exam wasn't that long, but I did get some emails from people said that still they had a little bit of trouble fitting into. I did get people finishing the exam and all that. Anyway, I have to think about that a little more. So I'll give you all the instructions on my final, final thinking about that, and maybe I'll try to give it a little extra time, even though I couldn't do that last time because there were some students that have something right after class. I remember getting one student sending me an email about that they couldn't really go over time that much. So I could do 5 or 10 minutes extra, but I couldn't do more than that, I guess. Okay, so right. So I'll have the final thing. I'll discuss what are the long format problem, all of that on Monday, and then we're still as you know that we have a break on Wednesday, Veterans Day, and exam will be on the 16th, as we mentioned. So for today, I want to finish up polishing a few things, and then I'm still going to give a bunch of problems for you to think about, and we're going to solve them together. But it's not directly the ones that are going to show up in this exam, but some of this stuff that I'm going to go over, yes, will show up. Remember, one problem will show up. And also in the final, we'll also have induction problems also. So I can't like give you the exam and then come back to chapter 29 already. I want to finish chapter 29. And also chapter 28, I left a little bit that I did not cover. I'm going to do that right now. It won't take me long. I'll finish up 29. I'm not doing Maxwell's equations. So chapter 29 won't take me long to finish. Then I have problems for you guys to look at and start more right-hand rules. But this is chapter 29, which is actually connected to chapter 28. You're doing the same right-hand rules, as you will see in a second. So even though it's chapter 29, a little bit of that will come in the exam. On top of it, some of the rules, the right-hand rules that you're using are the same. Let me just say, I did skip through this. I didn't want to get to it. Let me just make a comment. This is not going to be a major part of the exam, this part here. But this kind of stuff about the magnetism of materials is interesting. There are some things in there that are not intuitive, but they are kind of, you could think of them in terms of a classical picture, even though it's not really, as we said last time. This stuff is all, there was another chapter where we were discussing currents and resistances of materials, and I emphasized that you couldn't possibly understand, say, superconductivity with classical physics. That just doesn't make any sense. Right, Kuang, right. So yeah, somebody actually pointed, Kuang, I know you sent it to me privately, but I'll discuss it publicly. Wednesday is no class, it's Veterans Day. I had forgotten that myself last time, but Cecily reminded me of that. Okay, yes, so yes, definitely no class on Wednesday. Okay, right, so I'm not gonna get too much into this stuff but I wanna make a point that it is kind of helpful when you think about 16th, the 16th, Emma. Right, it couldn't be any other day because next Monday I'm going to tell you the questions that are going to be in the exam. Wednesday there is no class. The exam has to be the following time we meet, which is on the 16th. Right, Monday is the 9th, right? So the 16th for sure. Okay. Right. So I just wanted to say one comment about this business of magnetism. So when you have a magnet, let me just, this is not really correct, but it's just to give you an idea of how you can think about it, and this will help you in some of the questions we're going to encounter for the test bank of chapter 29. So if I have a magnet, and is the North Pole, and this is the South Pole. How we draw lines by having the magnetic field lines go from the north to the south, and you're supposed to put the arrow going from north to south. Okay, so you draw magnetic fields that look like that, and then the field lines go like that, like that. And this works like electric field lines. The closer they are to each other, the stronger the field is. So you're supposed to draw several lines. But I just wanted to point something out. When you have a magnet, you can simulate those field lines and make them look the same by, instead of having a magnet, putting a loop. So instead of having where there is a magnet, instead of that, you're putting a loop like this. And you put a current in the loop. And when you have a loop with current, that's the same thing as having a magnet. You know, it produces a magnetic field. And so what you have to realize then is the only thing is you have to choose the correct direction for the current. So as usual, it can be clockwise or counterclockwise. So if I make it go around this way, then I do my thumb rule. I put my thumb in the direction of the current. In the middle of the loop, my fingers point up in this direction. So if I draw it like this, then the field lines that come attached with the loop I drew this loop, and the field lines that come attached with this will go like this. And since in the middle they will be pointing up in this case, so it will go like that, and then it will come back through there. And likewise, it would go like that, and like that, like that, and go up. So it would go up this way, and it would come this way, and it would come that. So what I'm trying to tell you by doing this is that you can do a magnet, but a magnet is the property of materials, or you can do the same thing with a loop that has current in the right direction to simulate those field lines. And in fact, if you look into it a little more, this is quantum mechanics, so this is a little bit incorrect. But you have to realize that when you're talking about materials, you can think of it as an electron moving around an orbit, and then you would have orbitals, and you would start talking about chemistry or whatever else you want. All of that stuff is quantum physics, so this is not really a picture of it. But if you just want to think of it in a simple way to see where magnets are coming from, what's happening with magnets, then you could think of an electron moving around with some velocity, just like they do here, v, some velocity v. So a moving electron is a current, but you got to remember that the current is in the opposite direction. Okay, because current is the motion of positive charges, but in an atom, what's moving is the electron. The proton is not moving that much. The electron is going around, is much lighter, is going around much faster. So the electron is what's moving or whipping around. So the direction of motion of the electron is opposite to the direction of the current. So if the electron is moving that way, that means the current is going that way. That means this is the magnetic dipole here. This thing is the angular momentum. That's just the angular momentum of the electron going around. We're not talking about angular momentum right now. So there's not a lot of point of drawing that because we're not discussing angular momentum. But the bottom one, the orange thing going down, that would be the direction of the dipole moment, because the current would be going the opposite of what I drew over here. Okay, so this would be like clockwise. This one I drew over there would be counterclockwise. So, well, I mean, it's kind of like halfway, but okay, in any case, so you can again think of the magnet that the material produces by thinking of the motion of the electrons. I'm thinking about currents, and then realizing that when you have a current, that you produce a magnetic field. Moving charges produce magnetic fields. Okay, so this is a moving charge. We can think of it like a current or like a moving charge. Either way, that's how we discussed it. Okay, so in any case, so you can think of magnets in this way. You don't have to think of magnet as a bar. You can think of it like a current. So somehow there's a little electron that's producing a current, and that's responsible for the magnetic field. That does lead to, I'll be very brief about this. It's a little complicated, but there's several, now they're having to talk about quantum physics. Well, that's not really fair. Okay, you can't all of a sudden put quantum physics in there. Then they call Planck's constant. What the hell is that doing there? Well, that's quantum physics. So let's jump right through that. That's not. I don't think this is productive to stick a little bit of quantum physics in the middle of a PowerPoint slide. I'll just make a few comments that when when you have magnetic materials, there are several kinds of magnetic materials that you could have, and they describe a little bit what's going on here. So there are two different things that are going on here. There are actually three. There are paramagnets, diamagnets, and ferromagnets. So let me just very briefly, and just to give again, this is not an emphasis in the exam, but just to give a flavor for how what we've been talking about applies here. What you will be talking about is you have atoms, and they have these dipole moments because the electron is going around and around. And in some materials, the dipole moments of all the electrons are totally misaligned. Okay, if you put an overall magnetic field through that medium, then the dipoles of the electrons in this material will all of a sudden start aligning, and the material will become magnetized because now all the little electrons align their dipole moments, which is the magnetic field of the electron, with the external magnetic field that you're putting in the medium. Now, for some materials, when you remove the external electric field or magnetic field, then all the little electrons, their magnetic fields misalign again, and they get back and they're not magnetic anymore. For some of them, once you align them, they stay aligned. So those are the paramagnets and the ferromagnets. What happens when you align them? Some of them stay aligned, some of them, as soon as you remove the magnetic field, they misalign again, and the material doesn't stay magnetic. Now, what's interesting is actually for ferromagnets, like ferro means iron. So there's like iron, for instance, if you magnetize it, stays magnetic, but not forever, actually. It starts to demagnetize by itself. The temperature makes the spin, the little magnets of the little electrons, they start to misalign over time, and then it becomes non-magnetic again. But actually, that kind of makes sense, aligning all the little electrons so that they're all pointing in the same direction and produce an overall magnetic field. That's not too complicated. Actually, it turns out to be a third one that's actually also related to the subject that we're discussing. There are some that actually, if you put an overall magnetic field, then the magnetic properties of that material decrease instead of increasing. So something totally different must be going on there. And what's actually happening is, in this case, you're applying an overall magnetic field and you are inducing a current in the material which opposes the overall magnetic field. And so the material gets a little bit less magnetic. So it's kind of interesting, it's complicated. There are multiple things going on in this, but in the end, it's quantum physics, so let's not talk too much about it. But the bottom line for us, it's nice to think of magnets as currents. So basically, that's kind of like the takeaway. It kind of like, it helps to put things in it, so you don't think of a bar and that's it. You're actually just thinking of currents, and then you can try to see if you understand magnetic properties of materials that way. And it would still take you to quantum physics, and it would turn out that you don't quite understand it, but it helps to get there, to think of magnets as currents. And but for instance, it would help to understand why the Earth has a magnetic field. You need to think of that as a current, not like a thing that you stick at the middle of the Earth. Okay, anyway, so that's it. But we're done with that chapter. Chapter 29, what do we have left for chapter 29? Well, this was the thing that was going to show up in the exam. I'm actually going to have examples for this. In fact, I'm going to start with an example that is just like this from the test bank for chapter 29, which I've uploaded just now to Canvas. But I'm going to start, let's start with an example which is directly related to the exam to make sure you get something really, really relevant right away. And then we can do some of the other ones, some of the other examples they have in there, in that. So I'll show you the one I mean. But anyway, we're going to do an example just like this. I just wanted to tell you the rest of what's in this chapter, so I don't have to come back to it after the exam. I don't want to come back to this chapter. I just want to move on from here. After today, I'm done with the chapter after today. I don't have anything else to say about it. So we have ended up here. This is what's in the exam. As I said, we're going to have an example. This way of writing it, let's not worry too much about the example. We're going to have examples in a second. But this way of writing it looks different to what we had before, up here somewhere, right there. This is what we had before. This is Faraday's law. This is the number of turns in the solenoid, for instance. This is the flux, the change, the derivative of the flux, so on. And E is the electromotive force. But actually, you have to remember electromotive force just means voltage. And we can write a voltage this way as well. We actually gave that form of writing a long time ago. So this is just another way of writing the same thing. You would like to write things in calculus form because you want to come up with a set of equations that are perfectly consistent and that can get you to any example. You can treat every example. So of course, Maxwell's equations have basis on what it was before Maxwell. But Maxwell completed all the equations so that every case you could think of could be treated by a set of equations. Because as I said, it gets a little tricky here because now we just saw that a changing flux produces an electric field, which can do work. Well, so you have to be careful to make sure that every case is included in your equations. It turns out that based on this equation, you're not really doing a good job of being self-consistent and covering every case. So they're trying to tell you that here. I'll just very briefly mention it, but I won't. This all gets you to Maxwell's equations. But we already said that Maxwell's equations, that's crazy to put it in here. Maxwell's equations are, you know, it's math and it's calculus, and you got to think about every term in the equations and what it's doing there. And so that's not really, again, I don't feel it's fair to all of us stick it here at the end of this PowerPoint. If we had more time, yeah, it's very interesting, and it is classical physics, so it is conceivable to cover that. We're just not, that's not really, at this point, it would just be totally, it would take a lot of time to understand every term and what it's doing in equations, lots of examples to figure that out. I'm just gonna tell you that this Faraday's law, just to complete this chapter, this Faraday's law, while correct, is actually incomplete. That's what they're trying to tell you. This is Faraday's law. The above is also Faraday's law. It's a different form of the same equation. Okay, but they're actually trying to tell, what they're telling you here, all of a sudden they say, this displacement current, so kind of like abstract, what the hell? Okay, so what this wording is also not very clear. Let me reword it for you a little bit. They're trying to say to you, okay, if I take this Faraday's law and I have a wire, but the wire doesn't connect through to the other side. Rather, I have a capacitor in the middle. So in between the capacitor, there would be an electric field. But here in the middle, there is no current. There is nothing flying from one side to the other. So there is no current. If I build a capacitor, there is current moving into one plate, and then there's more current moving out of the other plate. But there's no current in between. So when you try to use Faraday's law in a situation like that, just a simple capacitor, you will find that if you chose the wrong path, you won't get the same result. So what they're trying to say is if you choose a path where this is the current that goes through my path, then I get a particular value. But if I then, instead of using this as my surface, then I bulge it out and I go inside this thing, then what they're saying, well, in there is no current. I'm getting in trouble here. Well, of course, they've solved this trouble. To solve this trouble, let's not get too much into it again. I will have to give you examples even of this. But they're just saying, look, to deal with situations in which you can use Faraday's law inside the plates, in between the plates, where there is no current, then you need another term in that equation. Otherwise, you're not going to get the same result. Depending which path you choose, you will get a different result. But if you want to have something, you get the same result no matter what, then you need to put a term into the equations that goes like this. So this is the change in flux of the electric field. So in here, in between the capacitors, there is no current, but there is an electric field. So there is a changing electric field in here. So if you stick this term in Faraday's law, then you get something that's perfectly consistent and it works just fine in all situations. But you need to add that term. So that's what Maxwell was doing when he came up with his equations. He was just thinking, okay, how do I write equations that apply in every case that because the electric fields produce changing electric fields produce magnetic fields, changing magnetic fields produce electric fields. So, you know, you want to go from everything to everything, apply it to everything. So when he came up with his Maxwell's equations, he could do that. You know, he couldn't find any flaw in the equations, and you can apply them in any situation and it will be fine. But based on what we've given so far, that's not really true. Okay, so you would have to complete things and fill up a few holes that are being left in here. And then you eventually would end up with Maxwell's equations, which are complete. That's it, you're done at that point. Okay, but since we're not going into Maxwell's equations, we can stop because that's what they're doing here. You know, now you have to start doing this, and then they say, well, you need all kinds of things. So let's stop here. And again, you're not responsible for Maxwell's equations. Hopefully that's clear. So from the rest of the class, let me just pick examples that will help you. So let me go right to the examples. Let's see. I just downloaded this one. Yeah. Let's start. Okay, actually, let's start with a few. I have one that is directly relevant. There is one below that is direct. How much time? Let's see. 1 second. I have one example later that's directly relevant, but we're doing okay with time. We can save that for a little later. Let's just go from the top here. This is all, you see, this is chapter 29, right? So once I'm done with this, and then I give you the one that's going to show up in the exam, one just like it. In fact, let's since you're probably more awake right now than you will be later on, let's start with that. I had the right instinct initially. Now I'm changing my mind. I'll change it again. Let's start with the one that's totally like the exam. And then I'll give you a little bit of time to think about it and to, okay, but that one. This one is very much like the exam. Okay? So, okay, so I just whizzed by. The answers are here, but I'm trying to hide them. I don't want to show you the answers yet. So please work on this for a little bit, not that long. This is directly relevant. I mean, I can't get any closer to the exam. For the exam, I might change the direction of the motion, or I might change the direction of the B field or something. But essentially, this is the exam question on this subject, on chapter 29. So please go, give it a try, have a thing, and if you find the answers, hopefully nobody was very fast and just looked at the answers when I flashed them just now. But if you find the answers, when you think you have the answers, please post them on the group chat. And again, the answers are on Canvas. Don't look at the answers. Again, this is just for you to figure out that you know what you're doing. So if you look at the answers, that's kind of defeats the purpose. Of course, it's not a problem, but that's not the idea. Okay, so give it a chance. Let's take like, I don't know, 10 minutes to do this, and then we'll move on. We'll go to the top and finish up things, and that's it. So 10, 15 at most, just give it a try, get started. I'll be right back. I'm gonna get a little bit more coffee. So if somebody thinks they got it, please put it up. Then we can see if you. Okay, that's for the force. How about the second one? It's at the bottom here, so all I have to do is scroll up. But how about the second part? How about you do that? And also, does it ask? Also, tell me which direction is the current, clockwise or counterclockwise? Even though it doesn't ask it, that's also going to be in the exam. Does it ask it? No, it doesn't. Okay, but anyways, it's good. It's good to figure it out. Yeah, it's asking, right. It's just asking how much power is being. The power goes to the resistor. Yes, so that's all I was asking. So you just have to remember what is the formula for power. And then finally, Emma, there's one more thing which is not asked for, but add it. Which direction would the current go? Okay, that's so. Let's see what other people think. Okay, everybody agree with those answers? Nobody disagrees? Well, let's roll it up. Okay, magnetic field is outward. This is the opposite as what was in the PowerPoint. In the PowerPoint, the current was going around counterclockwise. So yeah, this one would be clockwise. So that's not so tough. So again, please notice, so yeah, that's it. I mean, you got it. There's nothing, so it is clockwise and the applied force. Let me, in case you don't still quite together on the clockwise thing. Last time we had an issue because it seemed I was asking about the rod and some people were thinking about this part. Now, you can do whatever you want at any of the pieces of the circuit. So if I say it's clockwise, that means the current is here, the current goes that way, the current goes that way. So I could, to figure out the direction of the B field due to this current, I could use the top piece, or I could use this, or I could use that. In the middle is always going to give you, in the middle it gives you the same direction. This is a loop. It produces a magnet. I was just talking about that. A closed loop produces a magnetic field that looks like a magnet, pretty much. So this direction opposes the increase in flux, which is what you want, and that's correct. So that is the correct direction. Okay, so I don't know. That's pretty easy. So I'm gonna try, since I'm putting this from chapter 29. I don't want to make this one the tough question, so I'll keep this question as just basically this. I may ask a little bit something else. I don't know. I could try something else in there, but it will be essentially this. But notice what's happening though. What's happening is whatever the apply, if you say what is the applied force, you can actually figure this out. It's not that hard to do. You can say P equals VI, which is what you presumably you used. But actually you could also P equals FV, right? You could also do that. What I mean by that is that the power delivered to the power is being dissipated. This energy is being dissipated in the resistor. That's the only place that dissipates energy. But who's delivering this power to the circuit? Well, obviously it's you. There's a force on you that way against the rod that way. That's a magnetic force, and the applied force is just the person grabbing the rod or however you want to do it. But if you grab the rod and just move it, then it's your force that's delivering power, and that power is being dissipated in the resistor. So of course this P equals FV would have to be equal to the power, the voltage. So this is a different V, by the way. Sorry, make sure that this is the speed. F times velocity. I should have changed that velocity to something else. Let me change the symbol. So don't want to leave it like that, because that somebody might get confused when they look at the notes. So let me call this V, that's the speed. So this would be F times speed. And on this side, it would be voltage times the I. Well, in this case, the voltage we're calling the funny symbol E, which people call the electromotive force. So I should just replace that V with an E, I guess, to make it very clear what you're supposed to do here. Okay? Okay, there's nothing else here. So the power is delivered by the applied force. The power is dissipated in the resistor. Those two have to match up. Of course, there's nowhere else the energy is going. And the force on the rod due to the magnetic field, of course, has to be opposing you. It's not helping you move the rod. That wouldn't make sense. That would be a violation of energy conservation. So in the end, this Lenz's law that people talk about, this Lenz law about opposing the change in the flux, that comes down in the end to just energy conservation. If you use that, then you don't violate energy conservation. And that's it. That's why you need it, just to make sure of that. Okay, so that's it. There's nothing. I don't have anything else to say on this. Okay, if you have any questions though, because this is, as I said, in the exam. So no questions? Okay, let's go to the top to find a few other cases. These are more in the nature of multiple choice questions. Now I did remove some of the answers in there just to make sure you got it. So let's go through some of this chapter 29. That's the problem that's going to be in the exam. I'm not going to change it. That's it. But you know, I could also add some multiple choice questions. So that's so let's go through a few of them to try to communicate what's going on. See if we're on the same page there. So let's try to go a little faster on this. So again, as soon as somebody thinks they know the answer, we can go to the next, and so on. No one wants to take this up. All they're asking is which of these ones produce an EMF, so there will be a current in the loop For which of these cases will there be a current in the loop? All of them? None of them? By the way, some of these, sorry, crap. Some of these questions will also be in the final, as I said. Okay, Isaiah says B. Anybody else disagree with him? Agree with him? Which one would have a current? Which one is the one that induces a current and then also induces a B field? Okay. Okay, so B is correct. Let me explain that to make sure, to try to, if there was some ambiguity in this. Okay, again, what you're looking to do is to change the flux. If you're not changing, so how will you figure that out? Well, in the end, you just say this to yourself. I pick one time, and suppose I go through and I calculate the flux. You can make up fake numbers if you want. Then I pick a different time. Can I pick a different time at which the flux changed? Okay, so remember that the flux is B, but then you have to say dot A, and you're supposed to turn the area you're talking about, in this case the loop, into a vector. This vector is normal to the area that you're talking about. So what we agreed on is if you have the field like this, and the current, and this is the loop, sorry, and the field is like coming out of the board, that has a flux because the loop is being pierced by that B field. But you can tell in this case, it matters what the orientation is, because as I'm turning it, there will be a moment when the loop is sideways. I'm looking at it edge on now, and the B field is coming out straight like that. When the loop is like that, the flux is 0. So at some point is the maximum, BA, then it starts turning, and when it gets like that, it becomes 0. So the one that's turning is changing, the flux is changing because the dot is changing. So remember, to change the flux, you can change one of 3 things. You can change the B field, the magnitude of the B field. You can change the angle between the B field and the A vector. So you're changing the flux because you're changing the angle. And in the third case, the third possibility is you change the area of the loop. Well, this is not changing the areas of the loop, and the B field is not changing. So this is not changing, that the area itself is not changing, the loop is not increasing or decreasing. So the only thing you can possibly change is the dot. Okay, so what's changing the dot is case 2, because the dot changes because the B field stays the same direction, but the loop, the A vector changes as the loop changes direction. So this would be 0 B field, this would be maximum B field, maximum flux, sorry. Maximum flux, 0 flux, right? So this is correct. Only case 2, only, so answer, loop 2 only. The other ones are not changing the flux at all. At any time, the flux is the same as another time. Just because the thing is moving, the flux is not changing. You pick it here, you calculate the flux. You pick it here, you calculate the flux. It's the same flux. So the flux did not change. It's the same B field, the same area, the same angle. Okay? So yeah, okay, hopefully that's clear. Again, if it's not, something is not clear, these kind of questions will show up, as I just said that, in the final and also in this exam. So yeah, even though there's only one long format problem about this, these kinds of questions will show up. This one I don't like so much. What they're getting at here is that there could be other things changing beside the rate of change. Ignore this one, it's not really that useful. How about this one? This one is okay. Again, let's get through a few here. We can finish a little early. It's okay. I'm certainly decompressing. You're probably decompressing from last night as well. But let's do a few more. Let's get to at least 15 more minutes of this and try to answer a few of these. So you have a circular loop like that in the plane of the wire, and you have an increase in magnetic field that points out of the paper, and then which direction would clockwise or counterclockwise? Or clockwise then counterclockwise. Okay, everybody agree with C? Again, the direction of the current opposes the increase in the flux. So there is an increase in the flux outward. So if you oppose that, then would that be clockwise or counterclockwise? So Rogelio and Karat say C. Just let's do a couple more to see if we have full agreement here. A couple more people answering this question, I guess we can move on. Do you agree with that one? Nobody else wants to venture? Okay, let's break this down to make sure what the trouble is. Can I break it down? Let me ask a separate question, just to break it in two pieces. First, ask the direction, so just to figure out where is, obviously half the people said one thing, half the people so far said the other thing. So let me break it down into two pieces to make sure if I figure out which piece of that causes trouble. So instead of asking what is the direction of the current, let me pick a direction of the current and ask you a different question. Forget the part where it's asking about the increase in the flux. Let me just pick a loop like that and stipulate that the current is going around clockwise. I'm just asking you, in the middle of the loop, what direction would the B field, the induced B field, so this is a current, it produces a B field, in what direction would it be? Into the piece of paper or out of it? So into the board, into the computer screen or out of the computer screen? So say in or out. Okay, so we agree with that, right? So this one would be into the page. Okay, so we're in agreement here. Great, we got that part. You're totally right. So the B field due to this current would be, the induced field would be into the page. So now we go back to the beginning. This is the external field, not the induced field. Now you have to ask yourself, is the external field increasing or decreasing? Since the external field, in this case, they tell you the external field is increasing. So that means the flux is increasing. So I want to have to try to keep the flux low because I'm increasing the flux and this always opposes the flux. How do I oppose the increase in the flux? By pointing into the computer screen or out of the computer screen? How do I decrease the flux? Right, now we're on the right side now. Now forget the left side, we already got that part. Now on the right side, we're asking a different question. We're saying, okay, the flux is increasing out of the computer screen. How do I decrease the flux? It's increasing, so I have to try to stop it. but pointing into. So what I'm trying to get at is that this is the correct configuration to stop this from happening, right? So the answer would be clockwise, because this is clockwise. Again, what matters is that it says an increase in magnetic field. Okay, Trent, okay, good. So that helps. At least Trent was helped by that. Okay, so you break it up into two pieces. We all agree on this piece. That piece is easy. What's a little hard is to just say, is the magnetic field increasing or decreasing? If it's increasing, I have to try to decrease it. If I switch the words from increasing magnetic field, instead of that, I said decreasing magnetic field here. Then the direction of the current would have to flip, because now it's trying to keep the flux that it was. You're decreasing the field, so the flux is going down. So now I have to keep it up. So then I switch the direction of the current, and I'm trying to keep the flux that there was there in the first place. Correct. So it matters what I choose for this wording here. It definitely matters what I choose for that. Okay, let me show you another case, which is kind of like the same thing, but visually it's kind of challenging. We might get in trouble with this one just because I think, we'll see, but it's just visually it's hard. But let's do it well, let's actually, this one, the next problem is pretty much the same thing. Let's not do the same thing again. But how about this one? This one is a little tough because it combines two different things. But anyway, let's give it a try. It's kind of related. It's kind of like the same thing, but. Again, let's not do a lot of these because at some point, but let's do a few more, just we still have more time. So we can finish a little early to decompress. Let's see how many more we can do. Let's do at least this one, the one we're doing, also the next one, say, and then this one is the one that I think is visually a little challenging, but it does use the concept we've been saying. A magnet is the same thing as a loop. And so you can think of this thing as a magnet. You can think of this loop. You can replace this thing with a magnet if you want it. But for that, you have to know the directions. And then from the point of view of this person, where is the direction of the current? Okay, great. So that's kind of like the same thing again. And this is a magnet in this case. Okay, so we're going to do 3 more and that's it. And we can stop there. Okay, I'll let you look at that for a little bit. I'll be right back. Be right back. Okay, give it a try. Again, we have time. When we finish, let's give ourselves a goal of 3. When we've gone through 3, let's stop there. That's good for today. And then on Monday, I'll have more detailed things ready to instructions for the exam. Okay, we agree with D. Again, please keep in mind, it's kind of like the same thing. If you think about it, you can break it up into 2 pieces again. First, you say, what direction is the B field due to the wire? So let's do that piece first. Let's do the 2 pieces. I'm not disagreeing with anything you're saying. I'm just saying let's break it up into 2 pieces to make sure we got each piece correct. So then you would say this. You would say, okay, let's break it up first into the direction of the B field. Right. Yes. Actually, I'm going to tell you, yes, I think the same thing you do. Let's work it out. Make sure that we're correct. I think D is correct. But let's still work it out a piece at a time because just to make sure, that's it. So there are 2 pieces to it. So your first piece is, what is the direction of the B field? Then you have to decide, is the field increasing or decreasing? And then how do you counter that? So maybe you could divide it into 3 pieces. Okay, so the first part is, what is the direction of the B field? So I have a wire, the wire is going that way. So I'm putting my thumb in the direction of the current. My fingers above the wire, my fingers are coming out of the computer screen. But below the wire, my fingers are going into the computer screen. By putting my thumb along, below the wire, my fingers are pointed in. Above the wire, my fingers are pointed out. So if I'm just talking about the direction of the B field, that's the first part of the question. Then on the above, the direction of the B field would be out. And below, the direction of the B field would be in. And on the other one, the direction of the B field would be down, but that's correct. There would be no flux. So we don't have to worry about that one because there is no flux through that loop. Okay. So above is out, below is in. Great. So that's the first part. Great. So now we're saying what's happening to the current. So the current is decreasing. So the flux is decreasing. So now we have to try to keep the flux the way it was. So we want to help the flux. So in this case, the flux is out of the screen on the above case. So we want to help it because it's going down and we got to keep it up. So we want to give a B field that agrees with it, right? So that would be counterclockwise. So that's what I think that's A. So that's counterclockwise. So that counterclockwise would help the flux. And for below, clockwise would help the flux. So that's correct. Again, the flux below is into the computer screen. If you want to help that, then you got to do the clockwise motion of the current to help that flux. Okay? So I think it helps, in my opinion, it helps to break it up into 2 pieces. You do the first piece where you just figure out the direction of the field, that's it. And then the second piece, you have to figure out, am I trying to help the flux or slow or decrease the flux or fight the flux if you want? What am I trying to do? Since the flux is decreasing, then I'm trying to help it. If the flux were increasing, then I would try to fight it. Okay, that's it. Okay, by the way, if it's not quite clear, I'm trying my best to break it into pieces so that's clear to everybody. if I'm not getting a reaction from everybody, so I'm not able to tell if everybody is on the same page or not. So if you're not clear on it, what you could do is just go to I just posted this on Canvas. So the answer, I put one with answers, another one without answers. So you can just try it on your own, look at the answers. Still not clear, then you can ask me on Monday. We can do office hours on Monday. Office hours would be a good day. Monday would be a great day for office hours, I feel. So I'll stay around after class. And if you're still having trouble with any of this, let's clear it up for sure, individually. Okay. We said to do 2 more. Let's go ahead and do 2 more. At least let's start with this one, see what you think here. And then we can do 1 more. Let's see, a magnet here. This is kind of like the same thing. Okay, let's do this one, I guess. It's just kind of like the other one, though. It's kind of like the same thing. So the current is increasing with time at a constant rate. Which statement is true? Okay, let's just go ahead and do it, just to see if we all agree or not agree. But what statement is true here? Now remember, it's the same thing as before, I think, in my opinion. It's increasing in time now. So there is a flux, but now it's increasing, so you're trying to fight the increase. So which statement would be true? Okay, so let's break it up into pieces again, just like we did before. This is the same thing. It's a little simpler because there's only one loop, but you're increasing. The flux would come out up above the wire. The flux comes out of the board. Since you're increasing, you're trying to decrease that. So how do you decrease that? Clockwise or counterclockwise? It's increasing in time. So I'm trying to decrease the flux. Right. Okay, it's easy to get it wrong in the end, right? It's not, so in my opinion, the best thing for sure, I don't think you're getting the wrong idea. It's just that you have to go one step at a time until you get very comfortable with it. Otherwise, you keep making a little mistake, and then, because you got it's increasing with time. The field is coming up. So answer is actually A. Right. Okay. Let's go. Okay. The answers are online. So let's check it out. Let's do it again. Let's do this again. If you feel you need it at the end of next class, we'll do this again. Is there one more that we should do? This is kind of like the same thing. Let's stop here. Actually, it's more helpful if you try it a little bit on your own, and let's get on Monday. I'll come up with lots of exercises as I'm trying to do here, but more worked out problems. I'll give you more guidance. But again, one thing that might be helpful is to pretend that the exam is on Monday. And then, of course, the exam is not on Monday, but you could pretend it to yourself. Prepare as though the exam were on Monday, and then you'll have more questions for me. And I'll know better how to help you. But this particular section of I think this is just practice. If you practice it a little bit, then you will see how this goes. Let's do one more, and that's it. Okay, let's stop there. Let's do this one. How this one would this one go? Again, the way to think of it is, first you have to figure out what is the direction of the B field. How does the B field look? You have a current, it produces a B field. And then you have to say, well, if I draw the B field, how is it gonna look? And then am I increasing the flux or decreasing the flux? Then do I try to fight the flux? Okay, so let's do one more shot at this, and then we'll definitely stop there. This one is okay, I guess. So I'll give you time. Since we're only doing this, let's give you a little bit of time, and please, more people say what you think. see if we're close or not close to getting this right. Okay, what happened? Let's see. Okay, nobody else wants to. I'm visualizing right now. Let me think 1 second, make sure I got it right myself. Okay, this is a visualization one. Let's go step at a time, okay? Let's do a step at a time. If I'm drawing, you really need to the one wire is approaching the other one, right? So they have one here, and they're approaching this one. Okay, great. Now, you still have to know the direction of the B field, because you want to know in what direction is the flux. The flux is increasing, but in which direction? Into the loop or out of the loop? Okay, so let's do that part first. So let's forget the whole problem. I really do think, in my opinion, that you guys should break it up into two pieces. First, just figure out the direction of the B field. Okay, great. That's the first piece. The second piece is the flux increasing or decreasing? Okay, so first let's figure out the direction of the B field. You tell me the direction of the B field. Based on the current direction on this loop, how should I draw the B field? If I put a magnet, let's think about a different way. If I put a magnet instead of a loop, where is the North Pole, where is the South Pole of that magnet? To the right. Which, to the right is the what? Oh, right is the B field. That's what you're saying, Karan? Okay. He's saying that the right is the B field. So you would draw, based on what you said, you would draw the B field like this. So you could replace the loop. So the B field will look like this. It would go around this way and it would come back. And the arrow would go that way and that way. Correct? Is that what you said? One more yes, Karan. Do I get the right? Yes. Okay, great. Yeah, I agree with that. Okay, so that part of it doesn't seem so hard. You just do the one loop rule. You put your fingers. It's going through the middle of the loop. That's what you're interested in. And so it's going around and it's coming out of the loop like this, and it's going right in, and then it's going into the loop. And the north, so magnet pointed like this, north, south. Okay, so I could replace, so well, I think it's a visualization. Oh, I see. You're bringing the other side to the front? Which, okay, yeah, I see. Let's see. Let me erase this 1 second. See if the drawing makes it clear. Let's agree. Okay, you see, it's a visualization thing. Okay, let me tell you the visualization thing. What they're trying to tell you is, I agree that this is tricky when you do 3D problems. But you see that dashed line right there? What they're trying to say, by putting the dashed line over the wire on that end, they're trying to say that side is the far end. That side is far. And this side here is closer. Do you agree with that? That's what, yeah, I think maybe that's the problem. It's visualization. So you see they're putting a dashed line over the wire on that side. So that means that side is like that way. So it's kind of like the loop is like this, and the wire, so you're putting your fingers on the loop this way, and so your fingers point out. So I would have to agree with Karan. What they mean is that the B field, due to that loop, points to the right. Yeah, the visualization is a little challenging, but yeah, that's what they're trying to say. That's why they're putting the dashed line over the wire on the right side. Okay, so this B field would be like pointed that way. Okay, this one is a little tough. Okay, I'll have other examples. I'm running out of time, but I'll have other examples. But again, just look at the practice problems. Some of the ones we did are pretty easy, but let's finish this question then. So the B field points that way. So the B field is kind of pointing that way. Let's just consider the axis. It's a 3D thing, but to simplify, we're considering just the axis of symmetry, just the x-axis. So in the x-axis, the B field would point to the right, just like Karan said. Just on the axis itself, for sure, it would point to the right. Okay? That's the B field. Due to the second wire. So it's like north is on this side, and that on the axis that would point that way, and then it would point that way, just for the axis of the bar. So now you're bringing the other one closer and closer and closer. So you're increasing the flux because you're getting the two wires, they're getting closer. So the flux is increasing because the B field is getting stronger. When you get close to the magnet, the B field gets stronger. Okay, this is a flux to the right. So since you are increasing the flux, now you want to be able to decrease, to counter the flux, because you're increasing it by approaching the thing, you're increasing. So the induced field will try to counter the flux to keep it smaller. You're increasing it, the induced field tries to decrease it. So how will you do that? So in that case, the current will have to go that way. That counters the direction of the induced field, then counters the direction of the flux. So as seen from the eye, that would be clockwise. Is that what you guys said? It is. Oh, okay, good. So, okay, you had the right answer. Actually, all this time I wasn't sure I got the right answer. I'm happy to see that. Yeah, no problem. So that's good. That's yeah. Everybody said A. Okay, cool. Okay, excellent. So good place to stop because we're out of time. A is correct. Okay. All right. Okay. See you guys next time. I'll have things ready for the exam for next time for sure.